What we're going to do today is kind of a combo lecture in that some of it's going to be in YouTube and some of it's going to be on a talking PDF that I'll record with the document cam and my special notebook. Let me do something here. Hold on a second. Let me move this over a little bit. Okay. So we're going to recheck the energy table problem from one of them from homework 7. And then we're going to work on the space shuttle reentry and basic potential energy concepts. And along the way, we'll do some clicking. I just want to remind you today at 12:30, pretty much right after class, right? Right? Yeah, okay. SI, and then again on Monday at 4 o'clock for your study pleasure. And just as a general note to everyone, if you feel like you didn't do as well on exam 1 as you would like to have done, then you may feel like, well, I want to adjust my study procedures, my study methods. And one way that you can do that is that I always recommend is to have another student that you study with. And I was up here getting set up and I was watching 2 students up here in the second row. And they were just working on stuff together right there. And so if you make a friend here in class, or if you see a friend in class, or if you go to SI and make a friend there, then and then study outside of SI, outside of lecture with that person, once or twice a week, it's really going to help because it will help you sharpen up your thinking. If you think about it, every time, because when you're studying, you're going to be talking with each other. And if you're like most people, you exert a little bit of thought before you engage your mouth, before you speak. And so that forces you to think. So one of you may have a misconception, and without having a study partner, you might not know about it. But your study partner might say, oh no, Dr. B said do it this way. And then you correct each other. And the same thing for them. If they have a misconception, you might be able to correct them. And so that's the old principle, iron sharpens iron. So you want to be able to study together if you can. And SI is a great place to meet a study partner, and because you're working on homework and you're talking and blabbing. And of course, Yasmin is, pretty smart to talk to. Any human that you could talk to that is either a student or an expert like Yasmin or like me, or maybe somebody on your floor that took my class a couple semesters ago and crushed it, if you're in the dorms or something like that. Anything like that is going to be helpful. All right, now what we're going to do now is recheck the energy level questions from homework 7, the heavy basketball. And I'm going to do the gravitational potential energy at elevation 2 meters. And then I'm going to calculate kinetic energy with you. And then we're going to make part of the way of a computation of the actual speed. Now the speed was not a task in this homework, but it may be in the homework this weekend. All right. So let me pause the YouTube and we'll go to the document cam. And okay, we're back and we're back on the YouTube. Now, what I want to do now is go ahead and turn your clickers on. You're going to get a Go Nitro, and if you're on frequency DD. And now let's tackle a clicker question. Let's bring it all the way home now. I outlined on the document cam, that last line before I wrote etc. Let's bring it all the way home. Get V squared and then get V. So here's your task. Calculate the basketball's downward speed at height y equals 2 meters. Now it's going to be a good bundle of speed, so just calculate it to the nearest 0.1 meters per second. and then type in the numeric part. So there's an example of how to do that. Okay, so take a minute. And if you're sitting next to somebody, go ahead and consult with them. And, you know, if you're not sitting next to anybody, nobody's sitting next to you, God bless you. But if you are sitting next to somebody, definitely it's good now and permissible and encouraged to consult, kibitz, debate, etc. And we'll go, and I'll actually bring the calculation all the way home after, you know, you submit your answer. So go ahead and do that. Let me see what you guys are typing in. Remember, I want you to round it off to the nearest tenth of a meter per second. And remember, we're looking for V, not V squared. And also, you know what, let me turn the lights up. The decimal point is really, really hard to see on these clickers. So let me give you a full power. Make it easier for you to see that decimal point. It's one of the foibles of the iClicker, unfortunately. So I want something point something. Okay. I definitely consult with your, and then you'll have some homework to do the same thing over the weekend, plus other stuff. And so things will be really good. So you start crushing the homework, as I know you I know it's the desire of your heart to crush my exams and crush my homework. And that is also my desire to see you guys taking me to the cleaners, as the saying goes. And you can change your answer if you discover a blooper in it. Good, you guys are doing well. Okay, let me give you, think here. Let me give you another 90 seconds starting now. That would be a full 5 minutes. Got it? Good. One minute. Forty-five seconds. Good. I can see you guys kind of coordinating and talking with your neighbors and stuff. Good. You can't do it on the test, but here in lecture, yeah, perfectly fine. I encourage it because this is how you learn. It's how you learn how to think. And so on it, the more you can talk this over and talk it through, the faster you're going to be and the more confident you're going to be on exam 2. Did I say exam 2? Oh yeah. Better believe we're going to see something like this on exam 2 for sure. Okay, 10 seconds to go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Now I'm going to show you the results over here. Let me see if I can make this bigger. Hold on. Okay, that's a little bit bigger. All right, so there's 8.9. This is actually correct. 15.7, I don't know what that is. 78.4, I know what that is. So that would be like on an exam, that would be partial credit, like 1 point. Because they got the MG part right. Okay. 19.6, not sure. 15 points. Okay, you guys, there should be no negative signs because I'm asking for a speed. And I even phrased it as downward speed. 3.3, 3.9. All right, here's somebody that didn't round off correctly. So they would get like -1 instead of -2. Yeah, what is that 15.3 that keeps coming up? That's a little mysterious. Anyways, so this is how I look at your guys's stuff when I'm actually grading. Your exams. So let's go through the calculation. For those of you that didn't get it correct, here we go. Okay, so from the document cam, here's where we stopped before I wrote the word etc. 31.36 meters squared per second squared equals 0.400 times v squared. So to get v squared by itself, you divide both sides by 0.400. Okay, and that isolates Carlton. That isolates v squared now. Okay, so you got v squared by itself. Now you calculate. This is not your final calculation. This is v squared. Okay, so I know what that. So if you got to this point, you're good, but you forgot to hit the square root key because this is v squared, 78.4 meters squared per second squared. All right, so v itself is the square root of that mess, and that works out to 8.85 meters per second. And notice, mentally, I've got that meters squared per second squared inside the square root. All right, and then I've got the 78.4. So you got to square root numerically and get 8.85 for the square root of 78.4. But then mentally, you can just go meters per second over there. Question? That's correct. Mass will always be positive. V squared will always be positive. It depends on what you plug in. You could plug a velocity in. So if we knew that it was going to the left, at a certain speed, then you could put in, like negative 1.2 meters per second. You could put in negative 1.2 meters per second and then square that. But, square of a negative comes out positive. But yeah, mass is always positive. And kinetic energy is always going to be positive. All right, so 8.9 is your final answer for this one. All right. Now, there's going to be some questions on this for homework. And let's just review the strategy here. Once you set the baseline elevation y equals 0, then you can calculate a GPE at any height because your delta y is from the 0 point to whatever elevation that you choose, either 6 meters or 2 meters or 50 kilometers. And we're going to be doing the space shuttle here in a minute, and it's going to be 50 kilometers up. All right, so we're going to estimate the GPE of the space shuttle on orbit just before it comes down out of orbit. So that works out to minus mgy a lot of times. And then if you know the kinetic energy level, then at the top of the motion or at the bottom of the motion, so it's maximum at the bottom of the motion usually, and 0 at the top of the motion, because then it turns around and comes back down. But you might know it at some intermediate height, and if you do, then you can calculate total mechanical energy. So it goes like this: calculate GPE, calculate or be given kinetic, calculate total mechanical energy at that level. And then once you get to that level, you could figure out, you know that the kinetic, the total mechanical energy is that same number all the way down the table, all up and down the table. So you have ditto marks everywhere in the total mechanical energy column. All right, and then that lets you figure out kinetic energy at any other level, you know, the kinetic energy of the GPE at any other level. So you get your GPE value, then figure out, as we did, the kinetic energy, and then get a speed value. Kelsey. $47.04, yeah. Capital E, total mechanical energy. Because it's a constant of the motion. The total mechanical, that's what it means. The way that we set up GPE is that we're exchanging from kinetic to potential and back on the way up or on the way down. And when you've got your energy set up like that, then the sum of the two is going to be a constant at any point in the motion. So you have ditto marks in that column all the way through. But you got to get it calculated out at least one place. All right, which is, and at the top or at the bottom, it's usually fairly easily done because one of them's 0. Yeah. Okay. Another question? All right, let's keep going. So as I mentioned, you know, potential energy, it's an enormous tool for physicists, chemists too, and geologists. I mean, it's just it's an enormous tool. Let's go through another look at it, and this time we're gonna actually apply it to the space shuttle. So we know GPE equals minus mg delta y. So from ground, you know, so from sea level up to the plateau, delta y is positive. And so the GPE, by this formula, the GPE is positive or increases when delta y is positive. All right, you're increasing altitude. So when GPE increases, that means your kinetic energy decreases by the, you know, joule for joule. And that's what happens, you know, as you're going up, joule for joule, you lose joule after joule after joule until you've lost all your joules at the very top of the motion. All right, so, and it decreases, GPE decreases, you lose potential energy as you go down, as you lose altitude. So, so as I say, for every kilogram of mass of the object, and for every meter of altitude that you trade, you know, for or against, that you lose or that you gain, the GPE is defined at any elevation, once you know the mass and the altitude. And for that reason, we call it the energy of position. And there's a huge amount of calculus, really difficult calculus. I mean, if you follow this idea of potential energy all the way through, it takes you deep into quantum mechanics. and it's extremely difficult at that level. But we do it, you know, and try to figure out the Big Bang Theory and black holes and all kinds of stuff using quantum mechanics is quite challenging. All right, so there's kind of another review of kind of this concept of trading energies, you know, trading altitude for speed. You know, kinetic energy is the energy of motion. Potential energy is the energy of position. So you can think of the trajectory of an object as trading speed and altitude, speed and position in terms of energy. You know, and energy being the mode, the modus of exchange. Now, so that's just kind of a little conceptual outline, you know, to reinforce this generic idea of gravitational potential energy. And we're gonna, when we get in another week or two, when we start talking about electricity and magnetism, there's going to be EPE, electrical potential energy, and that's important in atoms because the atoms, the electron and the proton in the hydrogen atom, for instance, are bound by the electrical forces, and the electrical potential energy is well defined for hydrogen atom. And we find out that the energy levels of hydrogen electrons in hydrogen are very, very precise and give us a key insight into the world of quantum mechanics, the quantum world. But let's talk about bigger stuff now. Let's talk about the space shuttle re-entering the atmosphere. Now this is a false color infrared image taken from a big airliner. I think it's a Boeing 707 that they converted, the Air Force converted, or maybe NASA converted. They put a big infrared telescope in it and a big clear glass hatch that they could look through up at satellites and stuff. So they can you know, the Air Force can look at pretty much any satellite they want with that thing if they know where it is. And so they can look at the space shuttle coming in, and you can see the shape of the space shuttle, and you know, one of the leading edge. See the red one? That's because the space shuttle this is doing a maneuver called an S-turn. You know, you're up there at Mach 9.1, and you're taking turns. You know, they deorbit over the Indian Ocean, and by the time they're over the South Pacific, they can fly that baby. There's enough atmosphere that they can fly it. And you can see that there's a lot of atmosphere because it's getting hot. It's getting a lot of friction, okay? And at 9.1, at this altitude, the speed is about 7,000 miles per hour, all right? Now, orbital speed is about 18,000 miles per hour. So they're down from that, and so those guys, they're cranking turns with the space shuttle like you would if you were in a little Cessna. Except a Cessna, you can basically turn a Cessna on a dime pretty much, you know, as far as airplanes go. I mean, a 747, you need a couple miles to turn that baby. But a Cessna, you can turn it in a few hundred meters, easy. You know, when I was teaching down at the University of Virgin Islands, my office, it was the university there, the state land grant university for the U.S. Virgin Islands. It was an old Navy base right next to the airport, and the airport was an old air base, naval air station. And so I could go out of my office anytime I want, you know, get some fresh air, just, you know, take a break, and look at airplanes coming in, because I could throw a rock from my office. If I leaned out my office window, I could throw a rock through the window of the control tower. You know, we were way up the hill, and the control tower was really high, but it was about the same level and not too far away from my office. So it was that close. And it was always amazing to see the little Cessnas. You know, they're like bugs compared to these big jets that fly in there, you know, with all the tourists and stuff. You know, the 747s and the 757s and whatnot. And those Cessnas, boy, you know, they come in over the ocean to make their approach, and then they land. And it seems like they land in about 5 feet. They touch down, and then about 5 feet later, they're stopped, and then they taxi off to the side. Whereas the big jets, they go all the way to the end of the runway to stop, most of the way, anyways. So it's kind of amazing, the speed. Now this thing is no Cessna. It's a and it's definitely not a fighter jet, like an F-35 or something that's very agile in the sky. The space shuttle was not meant for agility. It was meant for, it's basically a truck, a flying truck, all right, a flying, semi truck. And so, but it can do S turns. So here's the cool thing about this: you're up there at 7,000 miles an hour, right? And I'll never forget it. The guys that did the first test flights, without any cargo of the space shuttle, they just launched it, took a few orbits, and then brought it back down. They were taking S turns. They come out of their orbit over the Indian Ocean. By the time they loop around into the South Pacific, now they're heading north towards California, but they start doing a couple S turns to burn off the speed, which is what you see here. And you know how at this speed, they do one S turn and they're already at Hawaii. So they start doing an S turn down by, underneath Australia or New Zealand. And by the time they're done with their S turn to burn off speed, they're coming in close over Hawaii. And then they do another one, to the right and bank it back over to cut across Texas and California and on their way to Florida. It's just amazing what these things do. Now, the height here, 160,900 feet, that's approximately 50 kilometers. So it's up there, but they can see it with this special infrared observatory. All right, so here's the specs. Let's work out the kinetic energy and the potential energy. All right, so our altitude is 50 kilometers, and we're going to go down to the landing strip at Kennedy Space Center. Now, you need a little bit of kinetic energy by the time you get down there. You're going to roll out at about, I think it's about 200 miles an hour. All right, so the mass of the STS is about 100 metric tons. So that's 100,000 kilograms. All right, a metric ton is 1,000 kilograms. All right, and the landing speed needs to be about 215 miles per hour, and then they hit the chutes and stuff, and then they roll out, and we'll call that 100 meters per second for a round number. So in meters per second, 215 miles per hour is pretty close to 100 meters per second. So now they're up there at 7,000 miles per hour, and they got to burn off a lot of kinetic energy and bring it in at 215 miles per hour. So they're going to radiate away a lot of heat into space. And, that's why it's got that black underside with all those thermal tiles and stuff. So let's say that from this altitude, it takes 12 minutes to get to the landing site at the Kennedy Space Center. So that's 720 seconds. So what that's going to tell us eventually is how many joules per second does the space shuttle have to dissipate into the atmosphere as it comes in. What's the rate of dissipating joules? And it's an enormous heat dissipation problem. So the question is how much energy is dissipated. We'll compute that. We have the technology. And the other question is how quickly was that energy dissipated? If we estimate about 12 minutes is righteous. That's a righteous number for the space shuttle. And it's not, like graven in stone, that they all take 12 minutes. But 12 minutes is typical for a space shuttle reentry. All right, so now that you've got your notes here, 50 kilometers and then 0 for the y-axis, 100 metric tons, and then we have the other speeds already up. So let's do the dynamical states at 50 kilometers, okay, kinetic and potential. All right, so here's my speed up there. Mach 9.1 is 3,130 meters per second. Pretty sweet. They're really, that's faster than any jet. It's just not even, the SR-71, the spy plane is the fastest plane we know of. It's not even close to that at its maximum speed. And so our delta y is 50,000 meters, 50 kilometers. All right, so we can figure out kinetic. So we have enough there. We have the mass. We have V1, 3130 meters per second. So we can figure out all this stuff. And the thing is, once we get kinetic and potential, we can tell the total energy as well. Now, it's got to be dissipated almost to zero. It's going to be a very small amount, relatively speaking, by the time it gets down to the landing facility at Kennedy. All right, and they used various braking methods to do that. Basically, trading altitude for kinetic energy and a lot of heat energy. So a lot of the energy is going to go dissipate into the atmosphere as heat. That's their energy management strategy. All right, so let's calculate kinetic energy 1 at 50 kilometers altitude. 1/2 mv squared, as always. And that's equal to 0.5 times 100,000 kilograms times 3130 meters per second quantity squared. All right, are you working? What's 3130 quantity squared? Go ahead and check that out on your calculator. It's going to be big. Anybody got a number? Okay, I see a few hands. Who's got a number? 3130 quantity squared. What do you got? Got it? 3130 quantity squared. Who's got it? Okay, in the back. Dude, you're burning me. You're burning my grits over here. Carlton. Correct. All right, 9,796,900. And it's meters squared per second squared. Now, I haven't done any of the calculations yet. So this is kind of like doing it on pencil and paper, one step at a time. I mean, you could do it all at once. And right now you can pretty much do it. And you'll get, on your calculator, you'll get 4.898 times 10 to the 11. There'd be a little 11 up there. Better get used to using scientific notation. Who's got 4.898 and then a little 11? Okay. All right. So now I want to turn that into something times 10 to the minus times 10 to the 9. So I move the decimal point 2 digits to the right. So 489.8 and then 10 to the 9. Now 10 to the 9 is a billion. All right. So the kinetic energy is basically 490 billion joules. Right. So up there in number 1, kinetic energy at 50 kilometers, Mach 9.1. There you go. All right. 490 billion joules approximately. All right. Now let's do the GPE. All right. So this is, we already know how to do this, minus mg delta y. Okay. So here's the minus sign leading, then the mass, 100,000 kilograms, and then negative 9.8 meters per second squared, and then the height, 50,000 meters. Now, put a little side note to this. This is an estimate because the acceleration due to gravity up at 50 kilometers is going to be a little bit less than 9.8. All right, so this is kind of a brute force estimate, very, but it's good enough for government work. It's good enough for us. Okay. So, so up at 50,000, it might start at 9.72, and by the time it gets down to the ground, 9.80. So, but this is good enough for us for today. Okay, so now I basically what I do on this one is I take all my exponents out, my powers of 10, and then I have, so 100,000, that's 1 times 10 to the 5. 50,000 is 5 times 10 to the 4. All right, so I basically have a 10 to the 5 and a 10 to the 4. So I have 10 to the 9 total, and then 1 times 9.8 times 5. So I've kind of factored out my powers of 10. And again, I get a billion joules. But here, I've already only got 49. You know, the kinetic energy is 490 billion. GPE, still pretty big, but not that big. It's only 49 billion joules. All right. So there's our calculation there. So what that means is that the total mechanical energy at 50 kilometers is the sum of those two. So that's, what's 490 plus 49? 539. Okay. So your total energy is 539 joules. That's capital E. Now the kinetic energy on landing, I calculated it for you. It's 500 million joules. All right. And here's the calculation for it. Final kinetic energy, 1/2 mv squared. Okay, so this is the specs basically for using the landing strip out there at Kennedy. You know, hit the landing strip at about 100 and you're golden. You know, your chutes will work, you know, and you won't run off into the gator, you know, you won't be swimming with the gators to get out of the space shuttle. You know what would happen? That space shuttle is really hot when it comes off. So if it ever did, you know, God forbid it, and it never happened, but if it had, and it went off to the swamp at the end of the runway, you'd see a lot of steam rising up, you know, this explosive blast. You know, that might have blown apart the space shuttle, actually. Think about it. You know, to you know, catastrophically hit the cold water. You know, it fry up a bunch of gators and everything like that. But anyway, so here it is, 500 million. All right, so you've got to dissipate 538.5 billion joules and have 0.5 billion left over at landing. So it's pretty bodacious. So the energy dissipation required is 538.5 billion joules. And we want to do this in 12 seconds, or 12 minutes, 720 seconds. And, you know, I'll tell you what, you know, the space shuttle is designed with safety margins to be able to dissipate more than this. But let's see, the Columbia that came apart over Texas with all those astronauts aboard, it had a hole in the wing. And what that did is it caused that wing to be unstable and also to heat up, you know, enormously on reentry, much more than it was designed to. It had a hole about this big in it, you know, big enough to stick your head through, I guess. And it just, and as a result, they lost that wing, and then they lost everything. And the men and women on board were killed. But anyways, hopefully they can, you know, most of their flights, they dissipated all that energy very quickly. So here's our dissipation rate. Okay, delta E over delta T, 538.5 billion joules and 720 seconds in the denominator. All right, so you work out that little. So it's basically 0.748 billion joules per second. Delta E, the change in the energy. Yeah. So you know, when you're down there at Kennedy, you want 500 million kinetic, and technically you're at 0 GPE. So your total energy down there is 500 million joules. All right. See, this is the rate at which you've got to do that. Now, power is a physics term that means the rate of production or use or dissipation of energy. All right. So 1 joule per second is a watt. And if you pay the bills at your apartment or your house, or have you ever watched your parents paying their bills? The electric bill is in, so many cents per kilowatt hour. So 1,000 watts times 3,600 seconds is a kilowatt hour. And so that's a unit of energy. And so you're actually buying energy, not power, even though they call themselves power companies. Anyways, so that's a watt. So this is 0.748 billion watts. Now, a billion, the prefix for that is giga. So this is 0.748 gigawatts or gigawatts. I hear it pronounced both ways. So, you may say to yourself, Dr. B, what the is a gigawatt? Like Marty McFly in the Back to the Future movie. What is it, Doc? What is a gigawatt? Well, a gigawatt, here's Grand Coulee Dam out in Washington State. That's the Columbia River. And guess what that's doing? It's a dam that backs up water, about 100 feet of water, and then they let the water go through these big pipes. They spin turbines, and then the turbines spin electrical generators, and that gives hydroelectric power. So they're converting GPE into electrical energy. But that's about 550 feet tall. That's about 6.809 gigawatts of power there. So that's a big. The smokestacks power station in New York that I showed you last time is approximately 1 gigawatt of power. Grand Coulee, I've been to Grand Coulee. It's awesome. If you ever get a chance to go out west, do it. I mean, if you're from Florida and if you've never been out of the state, you will not believe the difference in the climate. Once you get past Kansas or so, once you get past like Nebraska and North Dakota, South Dakota, and into Montana, Colorado, Wyoming, New Mexico, oh my goodness, you will not want to leave it because most people here have never experienced a sunny day outside and it's not humid. A few times during the winter we have it, but out there you have it all year round. So in the winter, the winters are sunny and there's lots of snow and it's cold, but it's sunny. In the summers, it gets hot, but if you go, because it's so dry, you go under a shady tree, it's like being in an air-conditioned room. So most of the people don't, like here, how much of Florida would, if all air conditioners suddenly evaporated from the face of the earth, how big would the traffic jams be heading north out of Florida? I mean, it'd be overnight. Depopulate the state if you could take away the air conditioners. But out in Montana, boy, that's God's country out there, my friend. Trout fishing, grizzly bears, mountains, 10,000 feet and up. Oh my, snow. Snow is this white stuff that's formed from frozen rain. It accumulates, you ski on it, stuff's kind of nice. But oh my goodness. And Grand Coulee Dam, the Columbia Plateau, oh my goodness. Well, that's my travelogue minute for class today. So a gigawatt is the power that big power stations put out, and that's what the little old space shuttle has to dissipate. So it's quite a task, thermodynamic task. All right, let's dismiss a few minutes early today. There'll be some more homework 8 over the weekend. It'll be due on Tuesday, and you are dismissed. If you want your Scantron printout and did not get it the other day, you could sure come on up and get it because we have a few minutes extra today.